Hello students, myself Mohammad Ashraf, Department of Physics, Seekers Educational Services. Today we are going to talk about electric flux. Okay, so basically what is electric flux? Flux comes from a Latin word which means to flow. If you have an electric field, if you have an electric charge around it, okay, this charge will create electric fields around it, electric field lines around it. Okay, if you take a surface area near the charge particle, these electric field lines will pass through that surface area. Okay, so the number of electric field lines passing through a unit surface area, that is called electrical flux. Okay, if you have any charge, you have a combination of charges or a single charge, okay, it will create electric field around it. Okay, the field will have electric field lines. Okay, these field lines will pass through any surface area. Okay, the number of electric field lines passing through any surface area, that is called electric flux. Mathematically, how we represent electric flux? Electric flux is determined by E dot dA. Okay, that is the dot product of electric field and area vector. So it's a dot product of electric field and area vector. Okay, electric field is measured. Okay, we know that electric, for example, if I need to give you a detailed explanation, we know that electric, for example, if you see here, flux is E dot A. E is electric field, A is the area vector. It's a dot product of electric field and area. So we can also write it EA into cos theta. First of all, flux we represent by phi. Okay. If we have an electric flux, we represent with a small subscript E. Sometimes we have a magnetic flux also, because magnetic field is also creates magnetic field lines around it. Okay, that will magnetic field lines will also pass through any area, so that will also have magnetic flux. To separate magnetic flux, we represent it by phi b. Okay, so we are discussing electric flux. Okay, it's a dot product of electric field and area. It becomes EA cos theta. Now, what is this theta? This theta is basically the angle between electric field and area. Now you should be concerned what is the direction of area vector. So the direction of area vector is perpendicular to the surface of the area. Okay, so if you see this diagram, okay, this is the any surface. Okay, this shows the direction of electric field. This shows the direction of area vector, which is perpendicular to the surface. Okay, angle between them is theta. So flux will be EA cos theta. Okay, moving forward. Electric flux, if electric flux is constant, for example, if we have a surface area, if we have any surface area, for example, if you take any surface area, okay, if you take any part of the area of this surface, okay, flux through that part d phi will be E dot dA. Total flux will be integration of E dot dA. If electric field is constant, what we can do? We can bring this electric field out of the integration sign, and it will become the integration of the area. Okay, it will become EA. But only when electric field is constant. But sometimes, suppose if electric field is not constant, electric field is variable at all the points. Okay, the electric field is variable at all the points. It means flux then will have to integrate, d phi will have to integrate E dot dA. Fully will have to integrate. Sometimes we need to calculate the flux through a closed surface also. In that particular case, we will put a closed line here to show that we are calculating the flux through a closed surface. The main important thing which we have to study for our JEE examination, okay, is Gauss law, okay, which uses electric flux. That's why I discussed the electric flux first. Okay, what's Gauss law first? Okay, as the equation suggests, it relates with the total flux of electric field through a closed surface to the net charge enclosed by the surface. According to it, the total flux linked with the closed surface is given by 1 by epsilon naught times the charge enclosed by the closed surface. Okay, so if you didn't understand this statement, I will make you understand in a very easy way. Okay, what does it say that? It says that total flux through a closed surface. For example, if you see here, there is a closed surface here. Okay, if you keep a charge q here, it will create electric fields around it. As you can see, this is creating electric field around it. Okay, if you take any surface area of that closed surface, you can calculate the flux through that surface area. You can see as here. Okay, so you can calculate the flux through any surface area. This part, as you can see, we are calculating the electric flux through a small surface area. Then you can integrate the whole area. You can, after integrating the whole area, what you can do, after integrating the whole area, we can get the flux through the whole surface area. As I told you, the close sign here shows the electric flux through the closed surface area. Got it? This LHS shows, left hand side shows total flux through a closed surface area, which is equal to Q internal by epsilon naught. Actually, there is an epsilon naught missing here. Q internal by epsilon naught. Q internal is the internal charge enclosed by the surface, the closed surface, okay, which is also called sometimes Gaussian surface. Also, one thing you should be remembering, or also one thing you should note down, that on the LHS side, electric field represents the electric field due to all the charges present in the vicinity. It's not due to the electric charges in the inside the sphere or outside the sphere. It is the electric field. It's the sum of electric field due to all the charges present in the vicinity, whether it is inside the sphere or outside, whether it is inside the Gaussian surface or outside the Gaussian surface. And Q internal here represents only the charge which is enclosed by the Gaussian surface. So this is the basic mathematical expression of Gauss law. Okay, so these are the same things, just written in different words. Now, what are the applications of this Gauss law? The application of the Gauss law is to find the electric field with the help of the Gauss law. Okay, just now I explained. Just now I told you that E dot ds, total flux through a closed surface, is the electric field, is the area, is equal to Q internal divided by epsilon naught. Okay, so this thing can be used to find the electric field due to charge distribution. How? For example, let's take an easy case. For example, if we have a charged particle Q, got it? And we have to find electric field at a point P, suppose, which is at a distance of r. Okay, we know that electric field will be created here. Some electric field will be due to this charge. Since it is a positive charge, electric field will be outwards, 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 outwards. Everywhere it will be outwards. Okay, at equal distance, electric field value will be same, because we know that electric field is inversely proportional to square of the distance. If you see here, electric field was how much? 1 by 4 pi epsilon naught q by r square. Okay, so at equal distance, value of electric field will be same. So we can assume that value of electric field here, if you draw a closed Gaussian surface looking like a sphere, electric field at all the points will be same. If we calculate the flux through a unit area, suppose d phi is equal to E dot ds or E dot dA. Okay, since if you see here, electric field is in this direction, area is also perpendicular to the surface, so area vector will be also in the same direction. Angle between them will be 0 degree. Cos 0 is 1, so it will become E dA cos 0. Cos 0 means 1. Okay, we have to calculate the total flux. So what we'll do? We'll put a integral sign. This will calculate total flux, which is equal to Q internal divided by epsilon naught. Got it? If you see here, E dA is equal to Q internal by epsilon naught. Okay. Now electric field is constant, so we can bring it out of the integration sign. Integration of area. Integration of area will be how much? If you see here, the surface area of a sphere is how much? 4 pi r square is equals to Q internal divided by epsilon naught. How much charge is enclosed inside this sphere? There is only one charge at the center, due to which electric field is created, that is Q. So that will be E into 4 pi r square is equals to Q by epsilon naught. Got it? So E will become how much? Q by 4 pi epsilon naught r square. 1 by 4 pi epsilon naught we also write as K, so it will become also K Q by r square. So we have seen through the electric charges also in the previous class also, that electric field comes kq by r square due to a point charge. From the Gauss law, it is also coming kq by r square. Moving forward, finding due to a spherical shell electric field outside the sphere. So just now we discussed, it will be done in the same way. Okay, we have a spherical shell, got it, and we have to find the electric field due to this spherical shell. Okay, at a point outside the spherical shell. Okay, so if you see here, we have a spherical shell made up of positive charges. Got it. We have to find the electric field at a distance of r from it. So if you see here, the mathematical expression, if you see, got it. Flux will be how much? E into 4 pi r square. Got it. We have integrated it. 4 pi r square. Area integration will be 4 pi r square. Got it. E into 4 pi r, which is equal to Q internal by epsilon naught. Internally, how much charge is enclosed? That is equal to Q. So Q by 4 pi epsilon naught r square. So E electric field outside will be Q by 4 pi epsilon naught r square. Same as we discussed the previous one. Electric field inside a spherical shell. What will be the electric field inside a spherical shell? So suppose if you have a spherical shell on which positive charges are distributed, and we have to find the electric field inside this shell only. Okay, so I can explain you better. For example, with this. So what is there? There is a shell. As there is a diagram also here, but I will better explain you. So there is a shell with some positive charges spread over here. Okay, we have to find the electric field at any internal point. For example, at this point. Got it? What we'll do? We'll make a Gaussian surface passing through this point. Okay. What does Gauss law say? E dot ds, total flux through a closed surface, is equals to Q internal divided by epsilon naught. If you calculate the flux through this part of the surface, okay, right hand side, if you write Q internal by epsilon naught, there is no charge contained in this Gaussian surface because charge is on the sphere here. So this part will become 0. 0 by epsilon naught, 0. Okay. So electric field will become 0. That's why electric field inside a spherical shell is also 0. Electric field due to an infinite line charge having uniformly distributed charge of density lambda. Okay, this one is interesting. Suppose if we have a line charge means a line which is made up of charges, simply like this. It's like this. Okay, we have a line which is made up of fully positive charges, and we have to find the electric field, suppose at this point P, which is at a distance of r. Okay, as you can see here also, we have a line charge. We have to find electric field at this point, which is at a distance of r. Okay, there is one term here, linear charge density, which is given as lambda. Linear charge density. What is linear charge density? So linear charge density is basically the charge distributed over the length of the wire. Okay, how much charge is distributed? Total charge, which will be equal to total charge divided by total length of the wire, which is represented by here lambda. Okay. Now suppose we have to find the electric field at this point P or this point P. So what we do here, we will make a Gaussian surface. Okay, everywhere we have to make a Gaussian surface. So we will make a Gaussian surface. This Gaussian surface will look like a cylinder. As you can see here in this diagram, in the slides diagram also, the Gaussian surface has been made in a cylindrical way. Okay, there how many surfaces we have? If you see this cylinder carefully, we have the upper surface, which is looking like a circle, which is not looking like it's exactly actually a circle. Okay, having radius of r. What will be its direction of area vector? It will be perpendicular to the surface. Similarly, we have a area vector downwards also. Its direction of area vector will be also perpendicular to the surface, and then we will have the curved surface. This one, this curved surface, this one. So we will have three surfaces: one upward surface, which is circular; lower surface, which is also circular; and then the curved surface. Okay. Electric field due to these line charges, if you see here, it will be like this in this direction. Due to this also in this direction. Got it? Area vector for this surface is perpendicular here. Angle between them 90 degree. Angle between them 90 degree. Flux is what? Flux is E dot ds. E dot dA, which is area. It means flux through these two upper surfaces, this one and this one, will become 0. Why? Because the angle between them is 90 degrees. So only the flux will be remaining through the curved surfaces. Okay, so through the curved surface, so which we have calculated here. You can see here E dot dA. E is electric field. We don't know the value of electric field, so I'm just putting the value E. Integration of dA. The curved surface area, total area of the curved surface is how much? 2 pi r into L. R is the radius, L is the length of the cylinder. Got it? So it will become E into 2 pi r L. Got it? It should be equal to Q internal by epsilon naught. How much charge is included in this Gaussian surface? So that will be equal to lambda into L, linear charge density into length of the cylinder, divided by epsilon naught. So you can see that E became how much? Lambda by 2 pi epsilon naught, or we can calculate 2 pi epsilon naught in terms of K also. It will become 2K by R. So in this way, you can find the electric field due to a linear charge while having density lambda at a distance of R from it. Moving forward, yeah, electric field due to infinite sheet of charge. Okay, so we have an infinite sheet of charge. It's like a whole sheet is made up of charges. So if you see the sheet, for example, if my hand is this sheet, okay, so you can see that the charges from here also, and you can see the charges from here also. So it will create electric field this direction also, and it will create electric field in this direction. Coming to the slide, if you see here, this is the sheet. Okay, this one is the sheet. So you can see this is made up of fully positive charges. You can calculate the electric field. If you see, it will create electric field at this point also, and it will create electric field at this point also. Okay. So what we are doing here, we will again take a Gaussian surface which is cylindrical. So we'll take a surface here on the sheet, okay, and we'll make a cylinder here, and we will make a cylinder opposite side of the sheet also. Same one, okay. So again, if you see, electric field is here in this direction. Area vector for this spherical surface will be in this direction. Electric field here is in this direction. Area vector will be also in this direction. Okay. Electric flux through the closed surface, through the curved surface of the cylinder will be 0 because angle between them will be 90 degrees. So only we will have flux through this circular area and this circular area. Okay. As you can see here, E into surface area of this one plus E into surface area of this one. 0, this one, 0, this signifies electric flux through the curved surface area of this cylinder, which is 0 actually, because the angle between electric field and area vector is 90 degree. So the total electric flux became here 2Es. Now moving forward, you see here, so the total electric flux becomes 2Es. Okay, left hand side clear. Right hand side, Q internal by epsilon naught. In Q internal, how much Q internal? Surface charge density, which is represented by sigma here, into area of the sheet. How much area we have taken? S. So sigma into S divided by epsilon naught. If you solve this equation, electric field will coming sigma by 2 epsilon naught. Electric field will be coming actually sigma by 2 epsilon naught, where sigma is the surface charge density, as you can see here also. So this was some of the applications of a Gauss law. We can use the Gauss law for finding the electric fields due to a line charge, due to a sheet, due to a spherical shell, okay, due to a point charge or any type of charge, okay, any type of charge distribution. The condition is that it should be symmetrical only, okay. The Gauss law will be valid, or you can apply Gauss law for finding the electrical field due to symmetrical charge distribution also. Otherwise, finding electric field will become a problematic. Okay. So this is it for today.